tonight, we may have solved some of those problems, but let's solve them for people that are on Zoom, the homework problems. And I probably can solve one or two maybe practice test problems, and the rest we're going to solve on Friday at noon, from noon to 1 o'clock here in this room. Informal, not required problem-solving session. So let's leave some of the practice test problems for that problem-solving session. Again, somebody has to be present and ask for those practice test problems, and we're going to solve as many as we can during this 1 hour problem solving. Okay, so don't forget we have a midterm on chapter 21, 22, and 23 on Monday. If you can attend the 11 o'clock class and take the midterm together with the 11 o'clock class, that will be great. If not, just come here and we're going to do the test. Okay, any remarks, any questions? If not, let's go with problem number 14 from the homework assignment. Problem number 14 from the homework assignment. So they say that you have an inductor and they give you the inductive reactance of this inductor. In other words, they implicitly give you the frequency at which this inductor is connected, the frequency of the generator to which this inductor is connected. Because you know that inductive reactance is 2 pi frequency times inductance. They give you the inductance and they give you the total, the inductive reactance. So from there you can say that frequency is just equal to that inductive reactance divided by 2 pi times the inductance. And this is the frequency that is going to be needed for later on. So keep in mind also that millihenry is 10 to the negative 3 and kilo ohms is 10 to the positive 3. Okay, so part B, now you have a capacitor that has exactly the same reactance that is given, that is for the reactance of the inductor. So they're asking what is its capacitance. Well, so if XC is exactly the same for my version 2.1 kilo ohms, you know that XC is equal to 1 divided by 2 pi frequency times capacitance. And therefore, the capacitance is going to be 1 divided by 2 pi frequency divided by the capacitance, capacitive reactance. So this gives you part B. Part C, they say, now you triple the frequency, how the reactance of the inductor and capacitor are going to change. So the new reactance of the inductor, well, here it is. You triple this, the new reactance of the inductor is going to triple. Here, right? Triple this, going to triple this. And in other words, from 2.1 kilo ohms, tripling it, you're going to get 6.3 kilo ohms. And the new reactance of the capacitor, if you triple the frequency. Well, if you triple the frequency, the capacitive reactance is going to drop by a factor of 3. In other words, instead of 2.1, it is going to be 0.7. kiloohms. Right? This is not a difficult question, but this is exercise about what is reactance and what is frequency and everything else. Okay, questions about this? If not, problem number 17, let's see what is problem 17. So you have a generator with given frequency in kilohertz, so 10 to the third hertz. They give you the current that it produces in a circuit that contains resistor and capacitor only. Find the voltage and find the phase angle. So we probably did this problem before. Let's quickly do it again. Problem number 17. So look. So this is the circuit that we're talking about, capacitor and resistor connected in series with a generator. They give you the frequency of this generator, and they say that it produces current. We can assume that this is RMS value of the current. So, well, if you are given the value of the capacitor, you can say that capacitive reactance is 1 divided by 2 pi frequency times the capacitance. And therefore, you can say that the impedance in this circuit is equal to square root of the resistance squared plus, well, XL is 0 and XC you just calculate it. So XL is 0 because you don't have an inductor. So from here you calculate the impedance of the circuit, and once you know the impedance of the circuit, you say that the voltage, RMS value, so it is not instantaneous value. Okay. I'm not going to put any subscript, but keep in mind, this voltage is not instantaneous value of the voltage. It's equal to the current, RMS value again, assuming that it is what they give us, times the impedance. So this should give you the correct, the answer that they expect there. Any remarks, any questions? So this is part A. So part B, you have to figure out, for part B, you have to figure out the phase angle. So they're not asking about the power factor, which is the cosine of the phase angle. They ask about the angle itself. And for the angle itself, instead of using the cosine, it is preferable to use tangent. And if you look at the formula list the formula that we derived using phasor diagrams, we showed that tangent of the phase angle is equal to XL minus XC divided by the resistance, I think. Let me make sure that I have it right. And once you have this value, the value of XC, XL is what we said. What is XL? 0. So keep this negative algebraic sign, otherwise you're not going to get the correct answer. So the angle itself is going to be inverse tangent of that expression. negative XC divided by the resistance. And this should give the correct angle. Make sure that your calculator is in degree. So you're going to get some negative angle. We haven't encountered negative angles in this textbook. This is probably the first time, but it matters. The negative angle shows that which one is the leading, the voltage or the current. And for this, in this case, what is the leading? You have, in this case, the current is lagging behind the voltage. This is what negative angle indicates. Yes.
Sorry, how did you know it was tangent of the angle instead of cosine again?
Well, the cosine is going to hide something for you. It is mostly trigonometry. Look, here is the unit circle. So if you have trigonometry, if the angle is negative, the cosine of negative angle and the cosine of a positive angle with the same magnitude have the same value. So the cosine is going to hide the algebraic sign if you are not lucky. While the tangent is not going to hide that. So always when they're asking for an angle, you always have to use tangent instead of sine or cosine. And again, trigonometry tells me that so from trigonometry, you know the cosine of phi is the same as cosine of negative phi. They have the same cosine. And if I calculate the cosine, I don't know if the angle is positive or negative. With the tangent, you don't have this ambiguity. You don't need to. And so trigonometry is not a required prerequisite for this class. Okay, other questions? Anybody? Okay, so from this list of practice test problems, let's choose one problem, and after that, maybe two. And after that, we have to go through chapter 24. Which of this list of practice test problems would you choose? So I assume that the homework problems are done and you can finish the homework assignment, right? Okay, so practice test. Which one? Or two?
Can you just go over 18?
Okay, let's look at problem number 18 from the practice test. Yeah, okay. So you have a generator and they give you the RMS voltage and the frequency of this generator, and you have a full RCL circuit. The value of the inductance, capacitance, and the resistance are given. Figure out the voltage from the generator, the peak voltage from the generator, the capacitive reactance, the inductive reactance, many questions here. Okay, so problem 18. So here is the diagram with inductor L here. This is problem 18. Let's see. So you have the value of each of the circuit elements, you have the frequency, you have RMS voltage. So the voltage right here, RMS value is 180 volts. What is the peak voltage? So part A, you say that V naught is just equal to VRMS multiplied by square root of 2. That's it. So the first question is answered. The second question, capacitive and inductive reactance. So capacitive reactance is 1 divided by 2 pi frequency times the capacitance. And inductive reactance is 2 pi frequency times the inductance. Again, keep in mind that microfarad is 10 to the negative 6. Everything else is clear. So, for this question, you need a lot of work with calculator. And you have to know your calculator pretty well. Part B, what is the impedance? Well, of course, just use the definition for impedance, R squared plus XL minus XC. Yes. Part C, what is the peak value of the current? Well, the current is the same everywhere. And the value of the peak current is going to be voltage, peak value, divided by impedance. That's it.
Is this the 18th problem?
Yeah, this is problem 18, yes. From the practice test. Problem 18 from the practice test, not from the homework. C is the peak current. Okay, we just found it. So this is the peak current not only through the resistor, but in the entire circuit. This is what they don't need to say through the resistor. It is the peak current at all. Part D, phase angle. So again, for the phase angle, use tangent rather than cosine. So just like before, the angle is equal to inverse tangent of XL minus XC divided by the resistance. So let's start it here. Part D, okay. Average power supplied to the circuit. Average power supplied to the circuit. So you can do it in different ways. Well, you can say that average power is RMS value of the current squared times resistance, for example. But in a similar manner, RMS value, of course, of the current is going to be whatever you have in part C divided by square root of 2. So current RMS value is I naught amplitude divided by square root of 2. So this is going to give you have other options also, but this should work. You can investigate other options. Part D, part F. What are the peak values of voltages across inductor, resistor, and capacitor? So this one is, you have to be more careful. So here is where you measure voltage across a capacitor. Here you measure the voltage across the resistor and the voltage across the inductor. The inductor is right here. So put the voltmeter here for the capacitor, here for the resistor, and then here for the voltage across. And look, each of those voltages, so for example, the voltage across the capacitor is going to be equal, and they're asking about amplitude, not RMS. So voltage amplitude across the capacitor is going to be current, amplitude of the current, times capacitive reactance. And in a similar manner, the voltage across the resistor is going to be current amplitude times resistance, and the voltage across the inductor amplitude is current amplitude times XL. So this is practically almost everything that you can ask about RCL circuits in this problem. So if you feel comfortable with this problem, you know RCL circuits, more or less. Okay. Any remarks and questions? So again, the answers that are given, who knows if they're correct or not, but it is your job to check those answers and see if they're accurate. Okay, let's do one more problem maybe. One more problem of your choice again.
I just have a question on wording of like some of the questions I was reading. For example, in both 3 and 5 on here, it says like a singular circular loop of radius 1 meter carries a current of 10 milliamps. It is placed in a uniform magnetic field of magnitude 5 teslas that is directed parallel to the plane of the loop. So that should tell you the angle, right?
Yes, this should tell you the angle between the normal to the loop plane of the loop, and the
So if it's parallel, wouldn't it be 0 degrees?
uh,
Because the answer, you should use 90 degrees.
yes, it is 90 degrees. So the angle is, look, you don't have a definition between for an angle between line and a plane. So when you're asked about an angle between a plane and some line, you mean the angle between the line and the normal to this plane. So always the angle is normal to the plane, and this is the vector representing the magnetic
I
field.
forgot about the normal to the plane. I was just looking at what,
Yeah.
how the plane was fitted, but it's
Yeah.
perpendicular to that plane.
Yeah.
Makes sense.
So this means that for the, yeah,
All right, that's not, we don't need to go over that question because it's fairly easy now. I was just.
Okay.
Familiar with the wording.
okay. So again, yes,
Wait, can we do another question? Number 6 is kind of confusing.
let's see. Okay, so let's do problem number 6. So again, but now, look, now the angle that you need in this problem is given on the diagram. Look, it is the angle between the normal to the plane of the loop and the magnetic field. So this angle is given, which simplifies your work. So problem number 6 from the practice test. So look, so you have a coil with 333 turns. So they don't show that coil, they just show one of the turns of this coil. And they give the cross-sectional area of this coil. In other words, they give the area of this circle.
Is it the area of all 333 together or just?
No, it is only one. So only this area, the area of this circle right here, the area of this circle is given. And this is what you need. You don't need any other area. So they give you the total resistance. So look, 300 turns means quite a long wire, and if the conductor is not a very good conductor, maybe some cheap, maybe steel wire, this means that it's going to have some resistance that is not zero. And they say that the resistance is 10.4 ohms. So they show the orientation of this coil with respect to external magnetic field. Some external magnetic field is present. They show it on the diagram. And they are asking, they say that the magnetic field changes its magnitude at certain rate in such a way that it induces a current that is 2.5 milliamperes. So what is the rate of change of magnetic field, of this external magnetic field? So here is the coil. You have some external magnetic field like this. But it is not permanent magnet, but a magnet that changes its strength. What should be the rate of change of the strength of that magnetic field? So that the induced current in this closed coil, it has to be closed in order for the current to flow. And look, this problem is a direct question about application of Faraday's law of induction. So the Faraday's law of induction says that the induced EMF, the induced voltage in this coil, well, without the minus sign, amplitude of that induced voltage, average value of magnitude, is equal to the rate of change of magnetic field flux, magnetic flux rate of change. This is induced voltage, average value, some average value. So the minus sign, again, I skipped, but I'm just looking for magnitude, so that's okay. And they're not asking about induced voltage, they're asking about the induced current, but the induced current is going to be that induced voltage divided by resistance, and the resistance is given. So you practically have to calculate the rate of change of magnetic flux divided by resistance, right? This is what. And now look, the magnetic flux is the number of turns in your coil, which is given, total magnetic flux, times area, cross-sectional area, times magnetic field, times cosine of the angle between the normal to the plane of the area and the magnetic field. So this angle is 50 degrees. I just will write it as 50 degrees. Okay. So this is This is what is needed. And look, the number of turns is a fixed number. The area, cross-sectional area of the coil is a fixed number. The cosine is a fixed number, so they can get out of the delta. They don't change. So you have an area and cosine out of the delta. And the magnetic field is changing, so it stays under the delta. All of this divided by time and divided by. So they're asking, what is this number? Delta B divided by delta T. This is what rate of change means, and this is what they're asking. So, in other words, they from here, since current is this expression, solving for delta B over delta T, you'll get it is going to be equal to the induced current, which is given, times the resistance, which is given, divided by number of turns, divided by area, and divided by also cosine of this 50 degree. This should be the answer. Yes.
How did R and delta T get on the bottom underneath magnetic flux?
So current is voltage divided by resistance, Ohm's law. But the voltage is this. I just replaced the voltage with its equal.
Oh, okay.
Right? And I wrote it in a slightly different way. That is. More questions here? Okay, so let's leave more practice test problems for Friday at noon here in this room. If you can make it, you're welcome to attend and ask more questions. Let's start chapter 24. It is important chapter. But it is based, again, that chapter is based on the previous chapters. And the main topic of the chapter is electromagnetic waves. So what is the definition for a wave? A wave is a pattern. So it is not something, by definition, it is not something material. It is some pattern of something. Pattern of whatever. Pattern of pressure variation, pattern of displacement of some object. Or in this case, in the case of electromagnetic wave, it is a pattern of electric and magnetic fields. And this pattern has to travel in space, and this pattern also inevitably carries energy, momentum, angular momentum, and eventually it carries information. So how let's consider the following. Exercise. Let's say that you have a generator right here of AC voltage, and here are the two terminals of this generator. And let's say that at the initial moment of time, this top terminal has negative voltage, highest possible negative voltage, in such a way that the voltage difference between the two terminals has maximum value at a certain moment of time. But so this means that On the upper terminal, you have, let's say, some negative electric charges, and on the terminal here, you have positive electric charges. But if you have electric charges, this means that you have also electric field between those charges. And electric field always originates from plus and into minus negative electric charges, into negative electric charges, from plus to minus. At a little bit later moment of time, your generator is still going to have negative and positive voltage on the two terminals, but the value of the voltage difference between the two terminals is going to be small, right? Here you have the maximum possible voltage difference. Here, the voltage difference between the two terminals is a little bit smaller. This means that you are going to have smaller number of electric charges, negative here, positive here on the two terminals. And therefore, you're going to have weaker electric field, maybe electric field represented with a vector that is with smaller magnitude, but still in direction up. However, the electric field that was between the terminal before, this electric field is not going to disappear. It is going to move away from the source, away from the terminals at the speed of light. So it's probably going to come somewhere here, let's say. So this is the old electric field. This is the new one that was just created. The old one is flying away from the source with the speed of light. So a little bit later, the voltage difference between the two terminals may be zero. So you're going to have zero voltage difference, zero electric field. But the two electric fields that were created before, they flew away from the source. So they are somewhere here. The two electric fields somewhere here, and you have zero created here. A little bit later moments of time, the polarity of the voltage between the terminals is going to be reversed. So you are going to have positive here, negative here, and therefore you're going to have electric field like this. The two electric fields that were generated before, they flew away, they came somewhere here maybe. So that you have zero. A little bit later again, the generator is going to get larger voltage difference with positive voltage on this terminal, negative voltage on this terminal, which corresponds to strong electric field in downward direction. And now you have those two flew away, they came here, the zero, and after that you have weak, and after that you have strong electric field in downward direction. So if you represent here the direction of motion of those electric field vectors, of course they are moving in all directions, but I'm just looking at those that are moving to the left or to the right. Those electric field vectors are going to cover an envelope like this. So they're going to, the electric field vectors are going to be like this. Here and later, here and here and here and here. Okay. So the electric field vectors are the vectors that I'm drawing. this. But it is easier to draw their envelope only. And this pattern of electric field vectors is moving away from the source with the speed of light in air, the speed c, the speed of light. So we already have a moving pattern of electric fields, but this is not all of it. In addition to that electric field, look what happens on the terminals of this generator. Well, here you have a lot of positive charges on this terminal and a lot of negative charges on this terminal. A little bit later, the number of charges dropped. This means that some electric charges that were on this terminal, positive charges, they moved and they canceled out some of the charges on the other terminal. In other words, a current flew. And when you have a current flowing, currents create magnetic field. This means that magnetic field was created in the transition from this picture to this picture. And if you use the right-hand rule, you can demonstrate that that magnetic field, well, on this side, it is going to be into the board, but in general, the general direction of that magnetic field is going to be into or out of the board, depending upon in which direction at this moment of time the current is flowing. So again, the generator is not connected to anything, but since the number of charges on its terminals change, you have a motion of electric charges. Electric charges cannot be created or destroyed. They just move and cancel out charges on the other terminal. The magnetic field created by these currents is going to fly away from the source, and the electric field vectors are going to have an envelope like this red envelope that I'm drawing. The magnetic field vectors are the red vectors. So B is the magnetic field, and the white vectors are the electric field vectors. Fine, like this. So now you have a pattern of electric and magnetic fields, and look, they cannot be separated. They go together because always when you have voltage difference, you have electric fields. But since this voltage difference changes, you also have currents, and therefore the magnetic field is generated, no matter if you want or not. So this pattern of electric and magnetic field traveling in space, we're going to demonstrate that this pattern carries energy. It carries also momentum and angular momentum, and this is what we call electromagnetic field. Yes.
So with the red, when it's like underneath the ground, if that's coming out of the board and on the top side is going into
So the electric fields are
sorry, the magnetic
oscillating in this direction. The magnetic fields are oscillating in directions perpendicular to the electric field, and also you can show perpendicular to the direction of motion. In other words, electric field perpendicular to magnetic field all the time, and electric field perpendicular to the, so let's say this is velocity, speed of light, so perpendicular, and magnetic field also perpendicular to velocity. So you have three perpendicular vectors. Just like X, Y, and Z. And you have to use again right-hand rule, but we don't want more rules. They are not introduced in the textbook, so I'll skip the rule. Okay, so look, this is something remarkable. Because depending upon the wavelength of this electromagnetic wave, you have familiar words, radio waves, TV signal, visible light, X-ray. So here is the wavelength here in this picture. So after this length, the pattern repeats itself. So this is the wavelength lambda. And the wavelength is connected with the frequency of oscillations. So if you stand somewhere right here, still, and you wait until this pattern comes through you, the number of up-downs that you are going to see per second is the frequency. And the connection between wavelength, frequency, and the speed of propagation is C divided by frequency. Now, if you look at this picture right here, if you look at this picture, if the wavelength is of the order of what I have drawn right here, so this is probably something like, what, 30 centimeters. Wavelength, electromagnetic wave with length of the order of 30 centimeters, we call radio wave in the FM part of the signal. So somewhere here we have FM radio waves. Longer wavelengths of the order of 100 meters is AM part of the spectrum, radio spectrum. So even longer wavelengths, we usually don't use them in electronics, but radio telescopes are sensitive to even longer wavelengths. Going to shorter wavelengths that are of the order of centimeter is what we call microwaves. This is the part of the spectrum that you have microwave ovens, the part of the spectrum that cell phone signal, for example, is. Even shorter wavelengths are what we call infrared. And infrared is not visible with your eyes, but your skin feels it. So when you go on the sun and you feel the warmth from the sun, the warmth is what we feel is actually infrared, and it can be actually image. You can actually make it visual signal by using infrared goggles, for example, light dark goggles that convert the infrared signal into a visible signal. Right? This is. Notice that the visible light is a very narrow spectrum wavelength range. Wavelength range between about 650 to about 400 nanometers. So 650 to 700 we perceive as visible light, and wavelengths of the order of 400 nanometers, 400 and something, we perceive as blue and violet color. Wavelengths between those we perceive as yellow, green, blue. the visible part of the spectrum. Wavelengths that are shorter than 400 nanometers, we perceive, well, they are ultraviolet. And you can divide the ultraviolet part of the spectrum to A, B, C if you want. After that, shorter wavelengths are X-rays, and even shorter wavelengths we call gamma rays. So next time, we're going to see that we already know how to detect those electromagnetic waves if they are not part of the visible spectrum. If they are part of the visible spectrum, you will see it. But if they are not, you build a loop like this, a capacitor, inductor, a closed loop like this, capacitance and inductor. And the resonant frequency of this capacitor, of this loop, is 1 divided by 2 pi square root of L times C. If this resonant frequency coincides with the frequency of the incoming electromagnetic wave, in that case, a current is going to start flowing in this resonant loop. You can take the signal from this loop, amplify it, decode it, and the result is going to be some radio station or picture TV signal. So we're going to continue with this on Friday. So any remarks and questions? So in that case, see you on Friday. Please work on the practice test, and the problems that are not clear from the practice test or any other source, please bring them on Friday for discussion.